So here we're going to talk about the law of large numbers in statistics. So if you toss a coin once, you cannot predict exactly how it will land. You can state only that the probability of a head is 0.5 because it has a 50% chance of landing on a head or a tail. If you toss the coin 100 times, you still cannot predict precisely how many heads will occur. However, you can reasonably expect to get heads close to 50% of the time. If you toss the coin 1,000 times, you can expect the proportion of heads to be even closer to 50%. In general, the more times you toss the coin, the closer the percentage of heads will be to exactly 50%. The idea that large numbers of events may show some pattern even while individual events are unpredictable is called the law of large numbers, or the law of averages. So the law of large numbers applies to a process for which the probability of an event A is the probability of A, and the results of repeated trials do not depend on results of earlier trials. That is, they are independent. The law of large numbers states, if the process is repeated through many trials, the proportion of the trials in which event A occurs will be close to the probability, which is P of A. The larger the number of trials, the closer the proportion should be to the probability of A. We can illustrate the law of large numbers with the die rolling experiment. The probability of a 1 on a single roll is the probability of 1 equals 1 out of 6, because remember there's 6 possible numbers to roll on a die, which will get you 0.167. To avoid the tedium of rolling the die many times, we can let a computer simulate random rolls of the die. The figure shows the results of a computer simulation of rolling a single die 5,000 times. The horizontal axis gives the number of rolls, and the height of the curve will give the proportion of ones. Although the curve bounces around when the number of rolls is small, for larger numbers of rolls, the proportion of ones approaches the probability of 0.167, just as predicted by the law of large numbers. So the figure shows the results of the computer simulation of rolling the single die 5,000 times. So here you've got your horizontal axis, gives your number of rolls, and the height of the curve gives the proportion of the ones. Although the curve bounces right here of the rolls, you can see that those larger number of rolls, the proportion of ones approaches the probability. So, and I see that those three things repeated on the two slides. Sorry about that. So here's the 5,000, but as it bounces around a little bit, as it gets further and further, it's getting to be that 0.167. So example 1, a roulette wheel has 38 numbers, 18 black, 18 red. The numbers 0 and 00 in green assume that all outcomes, the 38 numbers, have equal probability. What is the probability of getting a red number on any spin? Well, the theoretical probability of getting a red number on any spin will be the probability of A is equal to the number of ways red can occur and total number of outcomes. Remember, there are 38 outcomes and there were 18 red numbers. So 18 out of 38 is approximately 0.474. If patrons in a casino spin the wheel 100,000 times, how many times is a red number expected to result? Well, the law of large numbers tells us that as the game is played, more and more times, the proportion of times that a red number appears should get closer to 0.474. In 100,000 tries, the wheel should come up red close to 47.4% of the time, or about 4,400 times. And this would be true for black as well, because there's the same number of black ones. Expected value. So suppose the insurance company sells a special type of insurance that pays you $100,000 in the event that you quit your job because of serious illness. Based on data from past claims, the relative frequency probability that a policyholder will make a claim for the loss of a job is 1 in 500. Should the insurance company expect to earn a profit if it sells the policies for $250 each? Well, if InsureAll sells only a few policies, the profit or loss is unpredictable. For example, selling 100 policies for $250 each would generate a revenue of $25,000 because we take the 100 that we sold times 250 of each policy, we get $25,000. If none of the 100 policyholders files a claim, the company will make a tidy profit. However, if InsureAll must pay a $100,000 claim to even one policyholder, it will face a huge loss because if they have to pay $100,000 to one, and they only collected $25,000, then they're losing $75,000. In contrast, if InsureAll sells a large number of policies, the law of large numbers tells us that the proportion of policies for which claims will have to be paid should be very close to the 1 in 500 probability for a single policy. So, for example, if the company sells 1 million policies, it should expect the number of policyholders collecting on a 100,000 claim will be close to, this would be 1 million, the number of policies times 1 in 500, the probability of the 100,000 claim, which will be 2,000 claims. Paying these 2,000 claims will cost 2,000 times 100,000, which is 200 million. Now the cost is an average of $200 for each of the 1 million policies. Because there were 200 million, you had 1 million policies, so it's $200 for each of the 1 million policies, which means that if the policies sell for $250 or $250 each, the company should expect to earn an average of $250 minus $200 equals $50 per policy. And they sold 1 million policies, so they're still looking at a $50 million profit there. We call this average the expected value for each policy. Note that it is expected only if the company sells a large number of policies. So the expected value of a variable is the weighted average of all its possible values. Because it is an average, the expected value is likely to be close to the actual value, only when there are a large number of events, so that the law of numbers comes into play. So we can find the same expected value with a more formal procedure. The insurance example involves 2 distinct events, each with a particular probability and value for the company. In the event that a person buys a policy, the value to the company is the $250 price of the policy. The probability of this event is 1 because everyone who buys a policy pays the $250. In the event that a person is paid for a claim, the value to the company is $100,000. It is, or negative $100,000. It is negative because the company loses $100,000 in the case. The probability of this event is 1 out of 500. We now multiply the value of each event by its probability and add the results to find the expected value of each insurance policy. So our expected value will be the $250, which is the value of the policy sale, times 1, because if somebody has a policy, they paid that, plus the negative $100,000, which is the value of the claim, times 1 out of 500. So that gets us $250 minus the $200, which equals $50. This expected profit of $50 per policy is the same answer we found earlier. Note that it amounts to a profit of $50 million on sales of 1 million policies. So let's calculate the expected value. Consider 2 events with its own value and probability. The expected value based on the 2 events will be the value of event 1 times the probability of event 1 times the value of event 2 times the probability of event 2. This formula can be extended to any number of events by including more terms in the above sum. For example 2, suppose that $1 lottery tickets have the following probabilities and values: 1 in 5 to win a free ticket worth $1, 1 in 100 to win $5, 1 in 100,000 to win $1,000, and 1 in 10 million to win $1 million. What is the expected value of a lottery ticket? And discuss the implications. Now note, the winners do not get back the dollar they spent on the ticket. So here's our event. We purchased the ticket that has a negative dollar value. The probability is 1 because everybody who purchases a ticket pays that dollar. So negative $1 times 1 is equal to negative $1 for their value times their probability. If you won a free ticket, you get $1. The probability is 1 out of 5. So 1 times 1 out of 5 equals 20 cents. To win $5, it's got a value of $5. The probability is 1 out of 100. So we get a nickel. Win $1,000, it's 1 out of 100,000. So we end up with 1,000 times 1 over 100,000, which is a penny. And to win $1 million, the probability is 1 out of 10 million, and that equivalent is 10 cents. So the sum of the last column is negative 0.64 because we started with a negative dollar and it goes on down. So the easiest way to proceed is to make this table with all of the relevant events and their values and probabilities. We are calculating the expected value of a lottery ticket for the person who buys one ticket. The ticket price, therefore, has a negative value because it costs that person money while the values of the winning are positive. With all of the look at the probabilities and the cost, the expected value is the sum of all the products times their probability with the final column of the table. It shows that you're actually going to lose 64 cents. In other words, averaged over many tickets, you should expect to lose 64 cents for each lottery ticket that you buy. If you buy, say, 1,000 tickets, you should expect to lose about 1,000 times 64 cents, which is $640, which means you'll probably win about $360, but overall you're going to lose. And there are the people who win the big thing, so maybe they actually do come out ahead, but we're talking about what you should expect. Example 3, the art auction. You are at an art auction trying to decide whether to bid $50,000 for a particular painting. You believe that you have a 50% chance or 1 out of 2 probability of reselling the painting to a client in New York for $70,000 and a 1 in 4 chance or probability of reselling the painting to a client in San Francisco for $80,000. Otherwise, you will have to keep the painting, an option that has benefits, but not monetary ones. You get to keep a beautiful painting. What is the expected value of a $50,000 bid? Well, there are 3 relevant events to consider. With probability of 1, you pay $50,000 to buy the painting. This option represents a monetary loss to you, so it has a negative value. With the probability of 1 out of 2, you will sell the painting for $70,000. This option is a gain, so it has a positive value. With the probability of 1 out of 4, you will sell the painting for $80,000. This option is also a gain, so it also will have a positive value. So here's our expected value. The value of event 1 times the probability of event 1 plus your value of event 2 times the probability of event 2, the value of event 3 times the probability of event 3. So the probability of, or the value of event 1 was buying the painting. Remember, that has a negative value times the probability of 1, because if you buy it, that's it. There's 1 there. The $70,000 is times the probability of 1 out of 2, because you have a 1 out of 2 chance of selling it. And then the last one was the $80,000, a 1 out of 4 chance. So when we do the multiplication, we get 50,000 plus 35,000 plus 20,000, which will equal 5,000. So therefore, the expected value of $50,000 bid is going to be that. With a $50,000 bid, on average, you could expect to gain $5,000 by the purchase. It's important to remember that expected value refers to expected gain or loss over many such purchases. You should not expect to earn $5,000 in a single case because you're like, that doesn't make sense. Because if I sell it for $70,000, I make $20. If I sell it for $80,000, I'm going to make $30,000. But you're not always going to win, and so these are expected values. So the gambler's fallacy. Consider a simple game involving a coin toss. You win $1 if the coin lands heads, and you lose $1 if it lands tails. Suppose you toss the coin 100 times and get 45 heads and 55 tails, putting you $10 in the hole. Are you due for a streak of better luck? You probably recognize that the answer is no. Each coin toss is independent of previous tosses, so your past bad luck has no bearing on your future chances. However, many gamblers, especially compulsive gamblers, guess just the opposite. They believe that when their luck has been bad, it's due for a change. This mistaken belief is often called the gambler's fallacy or the gambler's ruin. So the gambler's fallacy is the mistaken belief that a streak of bad luck makes a person due for a streak of good luck, or that a streak of good luck will continue. One reason people succumb to the gambler's fallacy is a misunderstanding of the law of large numbers. In the coin toss game, the law of large numbers tells us that the proportion of heads tends to be closer to 50% for larger numbers of tosses. But this does not mean that you are likely to recover early losses. To see why, study the table, which shows the results from a computer simulation of large numbers of coin tosses. Note that the percentage of heads gets closer to exactly 50% as the number of tosses increases, just as the law of large number predicts. However, the last column, that at least for this particular simulation, the difference between the number of heads and the number of tails continued to grow, meaning that the losses, the difference between the numbers of heads and tails, grew larger even as the proportion of heads approached 50%. So here we have the number of tosses. So we went from 100 to 1,000 to 10,000 to 100,000. And you can see the number of heads and the percentage of heads. We started out with 45%, then 47%, then 49.5%, and 49.9%. The difference between the number of heads and tails. So here there was 10, here was 60, here was 100, here was 200. Now, even though the number gets larger, it's out of a larger number. So here you can see that it's changing, but it's still getting the percentage is about the same. So example 4, continued losses. You are playing the coin toss game in which you win $1 for heads and lose $1 for tails. After 100 tosses, you are $10 in the hole because you have 45 heads and 55 tails. You continue playing until you've tossed the coin 1,000 times, at which point you've gotten 480 heads and 520 tails. Is this result consistent with what we expect from the law of large numbers? Have you gained back any of your losses, and explain? Well, the proportion of heads in your first 100 tosses was 45% because it's 45 out of 100. We had 45 heads and 55 tails, so that's 100 tosses. After 1,000 tosses, the proportion of heads has increased to 480 out of 1,000 because 480 plus 520 gets us 1,000 tosses, or 48%. Because the proportion of heads moved closer to 50%, the results are consistent with what we expect from the law of large numbers. However, you've now won $480 for the 480 heads, and you've lost $520 for the 520 tails. That gives you a net loss of $40. Thus, your losses increased, despite the fact that the proportion of heads grew closer to 50%. They increased, because the value of what they cost and what you win. So another common misunderstanding that contributes to the gambler's fallacy involves expectations about streaks. Suppose you toss a coin 6 times and you see the outcome head, 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 which is all heads. Then you toss it 6 more times and see the outcome of head, tails, tails, head, tails, heads. Most people would say that the latter outcome is natural, while the streak of all heads is surprising. But in fact, both outcomes are equally likely. The total number of possible outcomes for 6 coins is 2 times 2 times 2 for 6 times, which equals 64. And every individual outcome has the same probability of 1 out of 64. Moreover, suppose you toss 6 heads and had to bet on the outcome of the next toss. You might think that given the run of heads, a tail is due on the next toss, but the probability of a head or tail in the next toss is still 50%. The coin has no memory of previous tosses. So example 5. A farmer knows that at this time of year in his part of the country, the probability of rain on a given day is 50%. It hasn't rained in 10 days, and he needs to decide whether to start irrigating. Is he justified in postponing irrigation because he is due for a rainy day? Well, the 10-day dry spell is unexpected, and like a gambler, the farmer is having a losing streak. However, if he assumes that weather events are independent from one day to the next, which it is often but not always the case, then the probability of rain is still a 50% on any given day, so he is not due for rain.